Okay, all right. So in last week's lecture, in our previous lecture, we have discussed about real gases, okay, deviation from ideal behavior. So there are two conditions that you should know, uh, which are at high pressure, at very high pressure, and also at very low temperature. The real gases, okay, tend to deviate from ideal behavior. So what are the ideal behavior? Okay, so a gas has negligible forces between its constituent atoms or molecule. That means there's no interparticle interaction between the molecules. And secondly, gas atom or molecules have negligible volumes. Okay, so these are the ideal gas model. Uh, that we assume all real gases behave, okay, but they uh, deviate as in these two, okay, these two assumptions are no longer valid, okay. These two assumptions are no longer valid at very high pressure and low temperature. That means at very high pressure, uh, there are forces between the molecules, and then the particle volume is no longer negligible. Okay, all right. So we also have discussed about how at high pressure and at low temperature they deviate from ideal behavior. Okay, all right. So it's because of at high pressure. That means to be specific, it should be at very high external pressure. Okay, at very high external pressure. Imagine we compress a piston. Okay, kita push down the piston further and further down, and what happens is that is what we call very high external pressure. Okay, so the volume is now decreasing. The distance between the particle is too small and the molecules are too crowded together. Okay, all right. So what happened in the container? Um, the We know that they become closer to one another, right? So they start to form ataupun develop the interparticle interaction. Okay, all right. So what happened to the pressure of the gas? The internal pressure. So just now we mentioned about external pressure, the one that we can control. Kita sebagai human can control. So that is what we call external pressure. The internal pressure is the pressure of the gas itself. So what happened when we compress ataupun we exert very high external pressure? Okay, the internal pressure or the pressure of the gas itself will in this case reduce. Kenapa dia reduce? Because all the molecules started to experience the interparticle attraction. So bila dia start to experience the interparticle attraction between them, okay, they dah start form. So when they collide the wall of the container, okay, they become slower. Sebab apa? Dia dah become heavy. Okay, dia kena carry dia punya orang kampung dia tu in order to in order to hit the wall, and then when they hit the wall, it's not as impactful as compared to kalau dia behave as ideal gas. Remember, kalau dia behave as ideal gas, we assume there is no interparticle attraction between them. We assume that there is no interparticle between them. Ataupun kita neglect lah, dia ada, it's just that dia tak significant because the gap ataupun the free space between the molecules are large enough, so that are large enough that we can neglect the interparticle interaction. Okay, so bila ada the interparticle interaction, this cause the pressure of the gas, the pressure of the gas to be reduced. Okay, and at low temperature, what happen is that they lose some energy ataupun the kinetic energy is now lowered. Okay, bila lowered, they tend to move slowly. Okay, slower. They tend to move slower, and when they come across one another, okay, they have enough time to interact. Sempat bertanya khabar lah sebab the movement is now slower. Okay, so they will tend to develop ataupun to create that interparticle attraction, and again when they collide between them ataupun collide with the wall of the container is not it will not be as impactful as compared to when they behave as ideal gas. Okay, so these are the two conditions that you should remember. Okay, you should memorize ataupun you should know. Okay, so these are the two conditions that the real gas deviate from ideal behavior. Okay, all right. So when these two are combined, okay, when this high pressure and very low temperature, when these two are combined, volume of particle becomes significant. Thus, all gases can be liquefied. Okay, when these two are combined at very low temperature and very high pressure, we keep compressing the gas. Okay, they come to a point that they will be liquefied. Maksudnya dah tak ada space between them. Okay, the free space between the gas particle are very, very small. Okay, and this will liquefy the gas. Okay, this will liquefy the gas. Okay, so we have discussed about these two. The representation of non-ideal behavior graphically. Okay, so as we go to the right of the x-axis, which is the pressure. Okay, which is the pressure become higher. So what happens is that the real gas, which in this case is argon, is deviated from the ideal gas. So the ideal gas is the red line, whereas the real gas, in this case argon, is the green line. So as you can see, it deviates. Okay, it deviates. So the green line deviates from the red lines at higher pressure. At lower pressure, as you can see, okay, they overlap with one another. That means we could say that that's why ideal behavior can be observed, okay, at lower pressure. Okay, at lower pressure. Same goes to temperature. Okay, ideal behavior can be observed at higher temperature. Okay, ideal behavior can be observed at higher temperature, but it deviates when the temperature is decreased. Okay, the temperature is decreased. As you can see, the graph deviates. Okay, the xenon line deviate from the ideal gas at lower temperature. Okay, all right. So please take note on that. The gas behave ideally at a higher temperature, okay, and lower pressure, lower external pressure. Okay, the gas deviates from ideal behavior when at lower temperature and higher pressure. Very high pressure and very low temperature. Okay, so make sure that you know what are the difference between this behavior lah. Okay, the conditions for each behavior. Okay, and then we also have this type of graph. As you can, again, this graph is just to show you that the real gases deviate. Okay, so these are the real gases. So they deviate from ideal behavior. So the ideal gas is the red one here. Okay, so as you can see, they all deviate from ideal behavior when the pressure are further increase. Okay, nampak tak? Cumanya they have different style. So ada yang going down first and then going up. Okay, and then ada yang going down earlier and then going up. Ada yang tak going down pun, dia straight away dia going up. Okay, macam yang helium ni, this is helium. Okay, ada yang slightly dia going down and then goes up. Okay, alright. So what are the causes that cause this graph macam ni? Apa penyebab? What are the main causes that cause this graph to be represented as this? Adalah dia punya factor-factor dia, because we have the intermolecular forces and also the molecular volume dekat situ kan. So the dua tu akan main peranan, okay, which we will look at later in the slides. Yep. Alright, so checkpoint 14, between SO2 and CO2, which gas will show a greater deviation from ideal behavior under the same condition, temperature and pressure? Explain your answer. Okay, alright, so this was your homework kan last time. So what would be your answer? Which one will show a greater deviation from ideal behavior? Is it SO2 ataupun CO2? What is your answer? Guys?
SO2.
Right, so my response, SO2. How about others?
SO2.
Saya takut saya tak unmute the mic. So selama ni saya bercakap seorang-seorang. Nasib baiklah saya mute. Saya on lah mic tu. Okay. Yeah. So far we have 2 responses. Okay. Saying SO2.
SO2.
Okay. SO2. Okay.
SO2. SO2.
Alright. Okay. Alright. So most of you answered SO2 as the one who which will deviate greater from ideal behavior. Okay, alright. So kita kena go back to the polarity of the molecule itself before we could identify. Okay, we could identify what are the causes that cause the deviation from ideal behavior. Okay, so SO2 and CO2. So CO2, we know that it is non-polar, whereas SO2 is a polar molecule. Okay, how do you know that? You have to draw lah. You have to draw. Okay, so by now simple molecule macam tu dah ada dalam otak dah. Okay, tak payah susah-susah dah nak lukis. Okay, that's why you have to do a lot of practices so that you become familiar and then you dah memorize lah. Somehow dia automatically, okay, memorize. Dia bukannya kita paksa, dia dah di embed in our brain. Alright, so SO2 is a polar molecule. So we have a non-polar and polar molecule. So polar molecule has dipole-dipole ataupun intermolecular forces that is stronger than a non-polar molecule. Okay, so that kalau the intermolecular forces is stronger, by right dia you imagine when they come closer to one another, they interact. So bila dia interact, the forces tu, kalau dia strong interaction between the molecule, okay, so by right dia punya dia become bulky tau, dia jadi berat lah, okay, because the forces is so kalau saya angkat call ni. Yeah. SO2 is a polar molecule, so SO2 by right has the strongest lah. A has the strongest intermolecular interaction compared to CO2. Okay, so stronger interaction, that means the more it will deviate from ideal behavior. Okay, the stronger the interaction between the particles, the more they will deviate from ideal behavior. Okay, that is one thing. Another factor would be the size. Okay, sebab in topic 4 kita tak go so much detail on the what type of intermolecular forces and what not tu. Kita tak go into detail, tapi kita list out all the possible factors, okay, that can cause the deviation to take place. So kita list out lah. Tapi it's good to know lah. It's good to know. Okay, the reason why SO2 and CO2, why SO2 deviate from ideal behavior is because it has dipole-dipole forces. We know that dipole-dipole forces is stronger than London dispersion forces that CO2 has. Okay, so itu kita dah belajar, so kita apply. Tapi in apa nama tu, in topic 4, what we are more interested in is on whether dia stronger intermolecular forces ataupun tak. That is all. Okay, and then kalau they both, okay, imagine if these two are non-polar molecule. So if they both have this the same polarity, which is non-polar, that means they have the same intermolecular forces kan. So what could be the other factors that contributes to greater deviation? So you kena tengok in terms of molar mass and also dia punya of their shape guys. Okay, alright. So ni dah quite obvious lah. SO2 is a polar molecule. That means it should have stronger intermolecular forces. Okay, and then SO2 has higher molar mass. Okay, sulfur kan duduk kat group 16 and then below kan, way below. Whereas carbon, CO2, group C, carbon come from group 14. Okay, the period 2, whereas sulfur come from period 3, okay, from group 16. So sulfur by right, SO2 has larger molar mass. Larger molar mass, that means it is a large molecule lah. Okay, it is a large molecule. Ataupun you boleh tambah kat situ larger molar mass compared to larger molar mass and has stronger intermolecular forces compared to CO2. Okay, right, moving on. Okay, so this is the slides. Basically, the slide, this following slides, okay, starting from this one, dia adalah the same thing that I have discussed to you in our previous lecture. Tapi this time around, we have slides to guide us on what the factors that cause the deviation to take place. Okay, hari tu ingat tak yang this first slide saya just cerita sebagai overview ni, slide ni. Tapi saya dah go very detail on each why high pressure dengan low temperature cause the deviation from ideal behavior. Okay, saya dah beritahu. Tapi kat slide ni sebenarnya dia ada in detail dah. So kita go through, okay, very briefly. Sebenarnya kita ulang balik so that you boleh lebih nampak lah. Okay, so it's actually benda yang sama that I have discussed during our previous lecture. And in fact, recap tadi, saya dah discuss juga. Okay, right. To describe real gas behavior more accurately, the pressure P and the volume V in the ideal gas equation need to be adjusted in order to account for the intermolecular forces and significant molecular volume. Okay, alright, so remember PV and RT ideally. Okay, apakah ideal behavior? Dua condition tu. Intermolecular forces is negligible, molecular volume is also negligible. Okay, alright. At high pressure and low temperature, okay, those two are no longer valid. Dia tak valid dah. Okay, so adakah sesuai we use PV and RT to describe the behavior of the real gas? Sesuai ke tak sesuai? It's no longer tak sesuai. Okay, it's no longer suitable to describe the real gas. Sebab real gas sekarang ni dah ada interparticle interaction and dah ada its own volume, so we cannot just simply neglect them. Okay, that means we have to alter, okay, we have to modify this ideal gas equation so that it is able to describe more accurately how the real gas behave. Faham tak? Ya, kita boleh guna PVNRT ni, tapi adakah dia akan describe accurately? Dia tak akan describe accurately lah. Okay, so kita nak able to describe the real gas at very high pressure dengan low temperature ni, we need to modify this ideal gas equation. Okay, kita kena adjust sebab yang kacau tu dekat sini P dengan V. Sebab P, ingat, kalau ideal gas kan kita assume tak ada interparticle attraction kan. So by right, the internal pressure, kita ada external pressure and we also have internal pressure. The internal pressure is the pressure of the gas. So kalau ideal gas, kita expect the internal pressure, the pressure of the gas will also be higher. Sebab apa? Sebab kita neglect the interparticle attraction. Tapi untuk real gas at high pressure and lower temperature, kita tak boleh neglect dah. Okay, so the pressure turns out to be lower. Faham tak? Sebab interparticle attraction tu dah, dia dah menarik, dia jadi berat, dia jadi slower, so dia punya pressure, dia langgar dinding pun tak kuat, so pressure will be lower. Okay, so pressure dah jadi rendah. Volume dekat situ macam mana? Okay, kan kita dah compress je kan. So the volume, the particle volume, each of the particle volume tu, dia dah accumulate space yang agak significant dekat situ. Dia dah rapat-rapat kan. So the volume is no longer negligible. Last time kita neglect because dia punya space tu terlampau besar kan between them. So we can just simply neglect ataupun kita assume there's macam tak significant langsung, as if macam dia zero. Sebab gap between them is too far apart. Okay, but this time around bila pressure very high dengan low temperature, the volume is no longer negligible sebab they start to have their own volume. Dia dah start ada dekat situ. In a way, the volume is now dah meningkat. Okay, last time kita abaikan sebab kita just pakai the volume of the container kan. So this time around, dia bukan zero. It's no longer negligible. Dia dah ada value dekat situ. So kita kena adjust this P and V in the ideal gas equation so that it describe accurately, more accurately, okay, in terms of the behavior of real gas, okay, especially at these two conditions, at very high pressure and lower temperature. Okay, alright. So, okay, we need some modification to be made on the ideal gas equation. Okay, so they need to be this factor need to be adjusted. Okay, kenapa nak adjust? Because we want to take into consideration for the intermolecular forces and significant molecular volume. Okay, kita kena consider these two. Last time kita tak consider. Now we have to consider. Okay, at these two conditions. Okay, very high pressure and low temperature. Okay, alright. So look at the diagram. So this is the initial, bukan initial, maksudnya when the gas behave ideally. Okay, pressure, external pressure dia low. Okay, ni normal condition. As you can see, the particles are too far apart to interact. Dia terlampau jauh. Gap dia tu agak jauh, okay, for them to be able to interact. So dia ada that interaction but not as significant lah. So we can just simply ignore. Okay, this is how the ideal gas initially lah. Okay, alright. So external pressure dia kita consider quite low. Alright, so what happen when we increase the external pressure? Kita push down. Macam mana nak increase kan? Kita push down lah. Kita compress. Okay, alright. So what happen is that the free space between the molecules are no longer as large compared to kalau dia dalam ideal gas ni. Dia jadi kecil, very restricted. The space is now very restricted. Okay, right. So they become closer to one another and they are able to interact. Bila they start to interact, interparticle attraction, we have red arrows there. Okay, lower the force of collision with the wall of the container. Okay, they become heavier. So when they want to collide with the wall of the container ataupun to collide among themselves, it is not as impactful. So bila tak impactful, what happened to the pressure, the internal pressure? The internal pressure goes down. Okay, so these are the points that I have discussed just now. So this is the first one. Okay, and this is the second. This is the third one. Okay, alright. So it's actually the same. Benda yang sama yang saya discuss tadi. Alright, moving on. Ada soalan ke? So far, how are you guys doing? This is in terms of the effect of intermolecular attraction. Okay, so this caused the pressure, the internal pressure to be decreased. Okay, mungkin boleh highlightkan dekat sini effect of P external high P external. Okay, high P external. Dia condition dia kan ada dua condition. So kat sini. Okay, kat sini cuba tengok number 3. As nearby molecules attract those approaching the container wall, reduces their force of impact on the wall, thus results in decreased gas pressure exerted to the container wall. So pressure of real gas is now less than that predicted by ideal gas law. Okay, alright. So P real at this condition should be less than the P ideal. Okay, this is the real situation lah. Last time kita expect the P ideal, okay, is higher. P real is higher, okay, ataupun sama dengan P ideal. Kenapa? Because we ignore the intermolecular forces between the particles. Okay, alright, moving on. Okay, so at very low temperature, just now we have high pressure. At very low temperature pula, the molecules move very slowly. So this allows the molecules to be close to each other for longer time to exert an attractive force to one another. Okay, so when they move slowly, they have time to interact with one another. Okay, to tanya khabar, apa khabar baik ke. So they develop that forces between them. Again, okay, dia akan jadi heavy. Okay, so dia dah slow down dekat situ and then ada interaction pula. So lagilah the pressure will be reduced. Okay, so these intermolecular forces between molecules, especially those hitting the gas P real is less than the P ideal. Okay, so this is in terms of the effect of molecular volume. Okay, tadi intermolecular forces. and dia punya effect on the pressure of the gas. Okay, now we are going to look at the effect of molecular volume. Okay, all right. So at normal pressure, the space between molecules or the free volume is enormous ataupun very large compared with the volume of the molecule themselves, like what we have here. Sama saja kat sini. Okay, this is at normal pressure, at our current pressure 1 ATM sekarang ni. So normally most of the gas behave almost ideally. Okay, so dia tak ada interaction between them. So dia punya space tu pun besar kan. So as you can see, how do we measure this particle volume? After all, they are far apart from one another. Macam nak measure dia punya particle volume ni? Okay, not like solid dengan liquid kan, they are closer. So kita boleh measure the particle punya volume. So but not for gas sebab dia jauh sangat. But sebab jauh sangat, so the volume of the molecule, this one. So compared with the volume of the molecule themselves. So dia punya ratio tu terlampau beza sangat, jauh sangat. Okay, so therefore that's why earlier on for the ideal gas, the free volume is approximately equal to the container of the volume. So V real is almost equal to V ideal. Maksudnya kita tak ambil the V real tau. Instead kita just consider the free volume. The free volume is approximately equal to the container of the volume. Kita simply ambil the V of the container. Kita tak ambil the particle volume. Okay, but as the applied pressure increases, free volume decreases. So imagine a piston just now. Okay, when we exert the pressure, okay, we increase the pressure, we keep pushing down the piston. Okay, so the free volume decreases. They become sempit. Okay, the space, the region become more restricted. Okay, the molecular volume makes up a greater proportion of the container volume. Okay, sebab dia dah rapat kan, they become closer to one another. So now they start to have their own volume, their own molecular volume, ataupun the molecular volume makes up a greater proportion of the container. Okay, look at here just now. Okay, so they start to have their own molecular volume compared to the volume of the container. So imagine, okay, earlier on, so this is the volume of the container. When they start to compress, okay, compress further down, so dia dah ada dia punya greater proportion of the molecular volume compared to the volume of the container. Okay, ni dah kira significant lah ni. Okay, so imagine if we push down further, so they become more closer to one another. So that's why dia boleh jadi liquid. Okay, right. Okay, so at very high pressure, the free volume becomes significantly less than the container of the volume. Okay, so at very high pressure, when we keep on compressing the the gas, the free volume becomes significantly less than the volume of the container. Right? Okay. So how do we describe this behavior of real gas, especially at very high pressure and at very low temperature? Okay. All right. So we cannot use PV and RT to accurately describe the behavior of this real gas. Kita boleh calculate, after all dia adalah calculation, tapi dia tak accurately describe lah, okay, the behavior of the real gas. So we have an equation that is known as van der Waals equation. So this van der Waals equation is used, okay, to describe the behavior of ideal gas accurately, sepatutnya. Okay, sebab van der Waals, I believe that you are familiar with the term of van der Waals, van der Waals attraction, van der Waals interaction kan, panggil? Van der Waals, the intermolecular forces, nama dia van der Waals intermolecular attraction. Tak silap saya lah. Tapi dia nama of the scientist. Okay, so this name, dia name after the scientist. Scientist tu nama dia Van der Waals. Okay, dia yang discover this intermolecular forces. Yang sewaktu dengannya lah and came up with this equation. Okay, right. So a modified ideal gas equation that accounts for attractive forces and molecular volume. It's actually apa nama tu, dia punya fundamental is still using the ideal gas equation. It's just that okay, we take into consideration the attractive forces and also the molecular volume. As you can see, dia sama PV and RT. It's just that kita alter on the P and also on the V. Okay, kita just alter sikit so that it would be apa nama tu, best to describe the real gas behavior. Okay, alright. So this is the equation that you should memorize ataupun you should hafal. Okay, P plus N2A over V2, V minus NB is equal to nRT. Okay, alright. So maybe some of you yang tak perasan tu mungkin tak perasan lah, kena balik baca lagi. Mungkin some of you akan wonder dekat sini. Tadi kata P real should be less than the P ideal. Okay, tapi kenapa dekat sini instead of minus, by right it should be less than the P ideal, betul tak? So to get less value, that means you should by right minus kan, minus N2A over V2. Okay, this is the factor lah. These are the correct in order to take account the attractive forces and the molecular volume. Okay, ini memang kena hafal. Ini factor A dia ni untuk intermolecular forces, for B for the molecular volume. Okay, alright. So this basically dia punya Van der Waals equation yang you kena memorize. Tapi just want to highlight here. Okay, so mungkin you wonder, okay, by right kan saya cakap P real should be less than P ideal. Bukan saya cakap kan, kat sini pun dah cakap. The P real or the P gas should be less than the P ideal. So by right, the value should be less. Okay, the value should be less. So how do we get less value than the P ideal? So by right, it should be minus. Betul tak? It should be minus. Tapi macam mana dia boleh dah ditambah dekat situ? Okay, jangan lupa dekat sini sebenarnya asalnya adalah ideal gas equation. Kita modify. Okay, alright, sebenarnya begini. Erase all lah. Okay, alright, so P real should be less than the P ideal because of the presence of intermolecular forces just now. Okay, alright, so supposedly P real should be P ideal to P ideal minus N2A over V2. Ini correction yang kita buat in order to get the P real. Okay, so this is the correction that we made. But kan kita nak masuk dalam ideal gas equation. So by right, instead of P real as our highlight, kita kena jadikan P ideal as our highlight because later on kita nak add into this ideal gas equation. So bila kita rearrange them, bukan ke awak akan dapat tambah there P real tambah N2A over V2. Okay, so this is the P ideal where we will insert into the ideal gas equation. So the P ideal is this. Nampak tak? So ini yang kita masukkan dalam the equation. Okay. So ini yang nak answer this to answer this question. P real is less than the P ideal. Yes, it is true. So supposedly if the P real is our highlight, then it should be like this. Should be minus. Sebab dia kena kurang patutnya. Okay, alright. Tapi since kita nak insert back into the formula of ideal gas equation, okay, so kita kena jadikan, we have to rearrange this so that the P ideal will be our highlight. So that's why kita rearrange P ideal is equal to P real plus N2A over V2. Okay, so this is the alteration that we made for pressure guys. Okay, kita dah alter the pressure, kita insert balik into the PV and RT equation. Okay, alright, same goes to V minus NB. Kenapa V minus NB? Kenapa tak tambah? Sebab initially kan last time kan, bukan last time, maksudnya in ideal gas equation, we neglect the value of we neglect the molecular volume as if macam dia tak significant at all. Macam nak kata zero. Okay, there's no molecular volume at all. Kita abaikan kan. But this time around at high pressure and low temperature, the molecular volume is no initially dia zero kalau kalau ideal gas, zero, negligible kan. So now at high pressure and low temperature, it's no longer negligible. Maksudnya dia dah ada, it is larger than zero. So by right, macam mana nak dapat the value larger than zero? So the only way is to tambah, betul tak? So sebenarnya again, okay, so sepatutnya V real, okay, is equal to V ideal, yang mana kita abaikan last time tu, macam kita kata di zero last time, okay, kita just consider the volume of the container, remember? So sekarang ni dia dah ada volume, so kita V tambah NB supposedly, okay, but again kita nak V ideal, we do not want the V real, okay, we arrange this into V ideal, okay, is equal to V real minus NB. Okay, this is the modification that we made in order to insert this P and V into the PV and RT gas equation, ideal gas equation, and this is what we ended up with. Okay, and this equation is what we call the van der Waals equation. Okay, faham ke? Faham tak situ?
Faham.
Faham
Faham.
Alhamdulillah. Dekat dalam, as you can see in this slide, we don't have this point dekat sini, dia tak ada. Ni, this one dia tak ada. Okay, ni pun dia tak ada, dia tak tunjuk. Tapi saja saya nak highlightkan, in case kalau yang betul-betul faham tu, mesti akan wonder. Tadi dia kata P real less than P ideal, tapi kenapa sini tambah dekat situ? Kan, sebab this one is to describe P ideal. Ni yang kita dah kasih adjust kat situ. Okay, after all we are using the PV and RT ideal gas equation. Okay, okay, so each correction terms includes a constant that has a specific values for every gas. Okay, that means different gas may have different A constant. So A constant, okay, is added into the equation, okay, because we want to take into consideration of the intermolecular forces that are present between the molecule. Okay, A ni describe the intermolecular forces. Okay, whereas B is the constant that we use. Mana ni? B is the constant that we use to describe the molecular volume. Okay, alright. So this is the correction factors for van der Waals equation. So the V and P, okay, are now changed into V minus NB, P plus N2A over V2. Okay, make sure that you memorize this formula. Okay, the P tambah N2A, bukan Na2. Okay, make sure that you get it correct. Okay, if not, you can imagine lah how severe your calculation. Okay, your working will be wrong lah, totally wrong. So sampai ke bawah because you have calculated wrongly. Okay, so please be careful in terms of dia punya formula dekat situ. Okay. Okay, like I said just now, okay, correction terms A relates to the strength of the attractive intermolecular forces. The strength, kekuatan the intermolecular forces, guys. So you can imagine, the larger the A, okay, the larger the value of E, by right, the stronger the intermolecular forces. How about B? Like I said, B relates to the mass of the gases ataupun atom, the gases atom or molecule, which, okay, we could represent it as molecular volume. So B describes the molecular volume. Okay, all right, so look at the table here. So as you can see, we have example of gases: helium, neon, argon, krypton, carbon dioxide, and ammonia. And then we have the constant, okay, A and B for each one of the gases. So as you can see, the constant increases down the table, going down the table. Same goes to B constant. The value increases going down the table. Okay, apakah maksud ini? So it shows that the larger the value, by right, we can imagine that the intermolecular forces is stronger, getting stronger. So yalah, NH3. And NH3 is a polar molecule. CO2, krypton, argon, neon, helium, these are all non-polar. So NH3, after all, NH3 has hydrogen bonding, kan? NH3 can form hydrogen bonding. So we know that hydrogen bonding is a strong, the strongest, okay, the strongest intermolecular forces. So that is why A punya value for NH3 is the largest. Okay, whereas, okay, if we were to compare between the non-polar and non-polar, okay, helium until carbon dioxide. Okay, as you can see, carbon dioxide punya value of A is the largest. Okay, alright, so what's the reason behind this? CO2, kat sini you kena consider. Okay, let's look at krypton. Krypton is 36. Okay, krypton dia punya molar mass is 36. Okay. They only have London dispersion forces. However, in terms of intermolecular forces, even though they ada the same London dispersion forces, but the strength of the London dispersion forces are different, berbeza. Okay, what causes that? Different in intermolecular forces punya strength? Okay, it's because of ada dua benda, sebab you kena consider, kan, in terms of the size, the molar mass, and also the size, the shape, man, surface area, kan, so shape, molar mass, and the shape ataupun the surface area. So obviously CO2, the molar mass is 44. Manalah saya punya 44. This one is 36. This one is argon is 18. Ya ke? 44, bukan. Salah. Dia punya molar mass is 83.8. Sorry. Krypton, kan? Betul tak? Carbon dioxide betul 44, tapi dah ilah Allah mana. This one is 33.8. Ini nampaknya besar, tapi kenapa this one has higher value of A? Okay, kat situ kita kena consider in terms of the surface area pula. Okay, CO2, okay, surface area dia tu is larger compared to krypton. Okay, even though krypton has higher molar mass than CO2, but CO2 has higher surface area. Okay, so that is one thing maybe explain on why A for CO2 is larger than krypton. Okay, but between the noble gases, okay, helium, neon, argon, and krypton, this one kita boleh explain in terms of molar masses. Betul tak? Krypton has higher molar mass than argon, neon and helium. So that is why nampak tak dia increase ni dia punya values dia increasing. As you can see, nampak tak? Dia tak sebesar macam A tau value dia. Dia 0.00000 dia ni, tapi dia still significant. Okay, imagine kalau during ideal gas, masa dia jadi ideal gas last time, it's zero kan. Assume macam tak ada at all. Okay, not significant at all. Macam there's no particle volume lah of for the gas. But now dia dah ada, even though dia 0.0 tapi still, okay, it is significant enough compared to zero. Okay, compared to zero. So kalau nak compare A dengan B, of course A ni nampak lebih besar, tapi this one kita kena consider in terms of last time dia zero, now dia dah ada values dekat situ. Okay, alright. Okay. Okay, so this is another representation of real gases, okay, in terms of graph. This is actually the same as this one shown to you just now, okay. So saya kan ada mention that kenapa some of the gases tu dia ke bawah dulu and then they goes up, okay. Kenapa yang ada straight ke atas, okay, tak lalu pun dekat bawah, okay, kenapa? Alright, so dekat situ we have to look at in terms of the dominance, okay, the priority dekat situ. Okay, let's look at the graph again. Okay, alright, so we are going to play around with the ratio of PV over RT. Okay, PV over RT ratio. Okay, kita ada dua possibility kan. It's either intermolecular attraction dengan molecular volume. Which one will be more dominant? Okay, alright, so kita nak explain kenapa dia dekat bawah ni. Okay, earlier on dia dekat sini, dia behave ideally, tak ada masalah. Tapi dia dah start deviate. Okay, they decrease further down and then after a certain point, they start to increase and then finally, dia dah overcome this ideal gas. Naik dekat atas. Okay, so kenapa? Why did this happen? Kenapa? How do you explain this? How do you explain this? Okay, ratio we are going to play with the ratio here. So gas, ideal gas, the ratio is 1. PV is equal to nRT. Okay, the ratio is 1. Okay, so kalau dia go lower than 1, that means dia akan ke bawah dekat situ. So by using the concept that we have learned earlier, pasal intermolecular forces and particle volume, how do we apply that in this condition? Macam mana nak apply, nak explain this graph? How do we explain this graph? Okay, right. Okay, bear with me sama-sama. Okay, the PV-RT ratio for the real gas is generally lower than ideal for low pressures. Okay, ini cuba ganti dekat add lah. Dia boleh lah pakai for, tapi somehow saya rasa add lebih dia punya it describe more lah, maksudnya describe lebih pada saya lebih faham lah tapi cuba fahamkan apa yang saya nak cakap apa maksud this statement. Okay, PV-RT ratio for the real gas is generally lower than ideal gas at low pressure. Okay, meaning the most important factor is the intermolecular forces ataupun intermolecular attraction. Okay, alright, so PVRT. Okay, low pressure. So here, okay, dia low pressure as in low pressure sebenarnya dia pressure dia lagi tinggi. Pressure dia, external pressure dia tinggi sebenarnya sebab kita compare this one at 400, okay, this one dengan at 600. Yang ni yang dia dah start naik ni. Nampak tak? Dia dah start naik. Dia sebenarnya tinggi pressure dia, tapi bila kita compare 300 dengan 600, for example, of course 600 is higher than 300. But 300 is already considered high external pressure. Faham tak? That's why dia letak inverted comma dekat situ. Low pressure not as in low pressure for ideal gas. So ideal gas kan behave ideal at low pressure kan. Bukan low pressure yang macam tu maksudnya. Okay, low pressure as in, you nampak tak perbezaan bila ni dekat sini dengan graf yang dekat sini dia dekat bawah. Bila pressure dah makin tinggi dia naik atas. Itu maksud low pressure dia kat situ. Okay, itu maksud low pressures dekat situ. Low pressures, ada S dekat situ. So these are considered low pressures. Tapi dia sebenarnya external pressure dia tinggi dah tau. Okay, we are talking about deviation from ideal behavior. Maksudnya dia punya external pressure dia tu dah memang tinggi. Maksudnya dia memang deviate. Ni nampak ni, dia deviate dah ni. Dia dah deviate. Okay, it's already deviating dah ni. Dia dah deviate. So that means this is at high pressure. Cuma high pressure tu, how high is high? Betul tak? Isunya, how high is high. So kita kena plot lah graf tu. So kita tengok. Okay, so this consider high dah ni. Tapi dia dekat bawah. Okay, alright. So dekat sini, case dia, intermolecular attraction is more dominant. Okay, now let's look at PVRT. Okay, kenapa kita kata dia more dominant? Kerana kita nak make sure dia dapat apa benda, nak tulis satu je pun. Okay, how do we get PVRT ratio to be less than 1? Macam mana nak dapatkan PV over RT less than 1? Kenapa less than 1? Sebab dia duduk bawah ni. Kenapa dia duduk bawah ni less than 1? Sebab this is 1. This is for ideal gas. Okay, tapi graf ni nampak dia duduk dekat bawah. Kalau dia duduk dekat bawah, that means it is less than 1. Betul tak? Okay, so dekat sini RT ni kita tak kacau. Yang kita boleh manipulate, bukan manipulate, maksudnya the deviation tu is caused by P ataupun V. Okay, alright, so macam mana, how do we get less than 1? It's either bukan, nak dapatkan less than 1, that means this value kena lebih kecil, betul tak? This PV value should be less ataupun smaller than RT value dekat bawah ni. Okay? Maksudnya kalau 1/2 kan atas lebih kecil daripada bawah, you akan dapat less than 1, betul tak? Okay? So, caranya begitu. Nak dapatkan less than 1, okay, bertambah nak dapatkan less than 1, maksudnya di atas ni, the denominator punya value should be smaller than this RT punya value. Okay, alright, so itu kita punya pegangan pertama. So how do we make sure that the PV values should be smaller? Okay, menggunakan understanding yang kita dah belajar tadi at high pressure dengan low temperature tadi, intermolecular effect tadi. Okay, P, kita cuba kita go through dua-dua. P can only decrease. Dia tak boleh naik sebab remember intermolecular forces, bila dia dah form, dia nak langgar dinding tu dia tak kuat dah. So that's why P dia reduce. That's why saya kata P can only reduce. Dia tak boleh naik. Okay, in this case dia tak boleh naik. V on the other hand, dia kena naik, dia tak boleh turun. Sebab apa? Bila at high pressure and low temperature, V will increase, betul tak? Because the molecular volume is now is no longer negligible. Dia dah ada its own molecular volume. That's why saya kata the molecular volume is now increases. Betul tak? Alright, so kita kena P ke V yang akan make sure that it should be less than 1. The answer should be P. Okay? So in order to get the value less than 1, the P value should be less. Betul tak? Kalau P value is less, barulah kita dapat value dekat atas ni less than 1. Okay? Faham tak? Faham eh? Okay. So kalau P tu less, apakah factor that cause the P to be less? Attraction. Okay? It's because of the intermolecular attraction. Yes, mungkin ada tanya, V tak berubah ke madam? V kan bertambah. Ya, dia bertambah, tapi it's not significant. We are talking about the significance of the effect. Mana yang lebih dominant? Intermolecular attraction ke ataupun volume punya effect? Kalau dia duduk dekat bawah ni, kalau dia ke bawah sikit, it shows that the intermolecular attraction is more dominant than the molecular volume. Okay. Alright. So, ini yang first statement yang dia cakap ni. So, ratio dia untuk nak dapatkan less than 1 macam mana? So, by right atas ni kena, value dia kena kecil kan. So, value dia kena kecil. Macam mana nak dapatkan value dia kecil? By right, the P should be less. Kenapa P kena less? Sebab intermolecular attraction dia tu, because of the dominance of intermolecular attraction. This cause the pressure to be less. Okay? Alright, so now, cuba kita tengok. Tiba-tiba, as you can see, tiba-tiba dekat sini, dia dah naik ke atas. Nampak tak? Dia dah naik ke atas. Kenapa dia naik ke atas tu? Apa reason dia naik ke atas tu? Padam. Okay? Biru. Okay, in fact dekat sini as you can see, dia dah turun kan. Sampai dekat sini, nampak tak dia dah start naik? Dia dah start naik dekat situ. Okay? Macam ni, tak ada. P tu dia menurun lebih banyak daripada V menaik. Faham tak? Okay, that's why saya kata dominant. Mana lebih dominant? Mana lebih dominant? P turun ke ataupun V naik? Mana arrow ni? Okay, P turun ke ataupun V naik? At high pressure and low temperature. In this case, dia dekat bawah tu, P turun tu lebih dominant daripada V tu increasing. Tapi as you can see, starting this point, okay, boleh dah nampak kan dia dah start menaik balik ni. Kenapa dia dah start menaik dekat situ? And then eventually, dia dah pass the ideal gas punya line dekat situ. Turun naik ke atas, ke atas. Okay, what caused this to happen? Okay, lagi sekali kita main dengan ratio. PV, RT. Okay, alright. So, dekat atas ni, up here, macam mana kita tahu dia more than 1. Because this is the red one represent the ideal gas. So, kenapa dia duduk dekat atas? Because it is more than 1. Alright, so sekarang ni, macam mana nak dapatkan the value should be more than 1? By right, value dekat atas ni kena lebih besar daripada dekat bawah, betul tak? Then only you get the value, the ratio is more than 1. Okay? Alright, so macam mana cara nak dapatkan more than 1 ni? P dengan V. P kita tak boleh increase kan? Sebab dia akan turun. Sebab case intermolecular forces tu, dia hanya boleh turun sahaja. Okay? On the other hand, V boleh naik. Kan? So the only way is dengan cara V increase. Okay, the molecular volume is now become more dominant. So starting from here, dia dah start dominant. Dominant as in P dia tetap turun. Tapi after a while, dia dah tak boleh turun lagi. Sebab imagine dia dah jadi liquid, katakanlah dia jadi liquid kan. Dia dah tak ada pressure dah dekat situ sebab dia dah dia dah form liquid. Okay, so dia dah form liquid, so the pressure become stagnant. So volume akan dia P akan decrease pun dia tak sesignificant lah compared to V. V akan keep on increasing. So V is more dominant when we are talking about this part of the graph. Okay, the volume most important factor is the molecular volume. Okay, P does play a role, but it is not significant compared to V when we are talking about this part of the graph. That's why dia kata is generally higher than ideal for high pressures. Maksudnya dah starting from this one, this part kat sini sebenarnya. Okay, dah start dominant dekat situ. Okay, sebab dia dah start naik dekat situ. So kat sini ke hujung tu, so dia, that's why dia kata high pressures. High pressures. Okay, pressure yang lebih tinggi compared to this part. Alright? Faham ke? How are you guys doing there?
Faham.
Faham Kita cuba applykan konsep ratio ya. That's the thing about graph ni Kalau dalam chemistry, it's not as simple as having graph. Okay, this is proportional, this is ni. Bukan macam tu lah. Dia tak sedirect macam tu. You must be able to read ataupun to explain how the graph end up macam tu. Okay, dia punya behind, dia punya hidden explanation dekat situ. Okay, so how do you apply the deviation from ideal behavior ni dekat high pressure dengan low temperature, okay, in terms of graph? Macam mana you describe that? This is how you describe. Okay, so you boleh imagine tak kalau graph ni, ni yang ke bawah ni, okay, yang ke atas, ke bawah sikit dia naik atas. So dekat sini ada, maksudnya kalau dia punya intermolecular forces tu, as you can see nampak? From here, okay, and then going towards the right, so even at higher pressure, barulah dia nak tunjuk volume punya dominance. Lambat lah, volume punya dominance tu lambat, starting here. Orang lain tu dah awal-awal kat sini dah tunjuk, dah menaik. Okay, volume punya effect tu dah dominant. So kat atas ni kita boleh kata, the volume effect is more dominant than the volume. Okay, so ni tak silap saya, water ni. Water kan kita tahu the intermolecular forces of water, one of it is, water has hydrogen bonding kan, it is the strongest kan. So this, another example lah, okay, yang mempunyai intermolecular effect yang dominant. Maksudnya dia ada strong intermolecular forces. Okay, alright. Okay, jom. Check point 15. Okay, based on the respective van der Waals constant, select the gas that is expected to behave more nearly like an ideal gas at high pressure. Explain your answer. Okay, alright. So, which one will behave nearly like an ideal gas? Is it argon or carbon dioxide? Given the constant for A and B for each gas. Which one do you think will behave nearly like an ideal gas? Argon ke carbon dioxide? Hello, saya tanya.
Argon.
Okay, how about the rest? How about the rest? What is your answer for this question? Alah, ni boleh jawab macam tu je lah. Nak buat apa? Orang nak buat calculation apa kat sini?
Argon maybe.
Argon, okay. Lagi?
Argon.
Argon.
Okay. Okay, all right. So most of you answered argon. Okay, may I know what's the reason behind it? What's the reason of what is your justification? Why do you choose argon?
Because it has weaker intermolecular forces and smaller
Sorry, tak
molecular
dengar.
volume. Weaker intermolecular forces and smaller molecular volume.
Okay, what do you use to justify the weaker intermolecular forces?
Because the A is smaller.
Yes. Okay, very good. Okay, by using from the constant given, we'll be able to determine whether they have this. We can determine the strength of intermolecular forces of the molecule of the gas. Okay, so kita pun tak payah susah-susah lah nak fikir apa kan, tapi we should know lah. Okay, after all, argon dengan carbon okay, argon and carbon dioxide, both of them are non-polar kan, so both of them also have London dispersion forces. Okay, alright, so itu just sajalah, kita kan dah belajar, we have learned that in topic 3. So kita apa nama tu, kita saja-saja nak initiate dalam kepala kita so that kita boleh make sure neuron-neuron tu berhubung. So dia ada connection topic 3 and topic 4. Cuma in topic 4, we are not going to go into detail on what type of intermolecular forces unless the question asks. Okay, tapi you should know lah sebab you dah belajar in topic 3. Okay, so for this one, sebenarnya soalan just nak based on the A given. Okay, so your answer should be argon. Kenapa? Because of the value of A for argon, value of A and B for argon is smaller than the value of carbon dioxide. Okay, so kenapa bila dia smaller, dia behave like more, dia behave more ideally. Okay, sebab itu this value represent the strength of intermolecular forces. Okay, alright, so we know that carbon dioxide and argon. Argon dia punya molar mass, kalau nak sajalah extra, molar mass of argon is 40. CO2 on the other hand is 44 dekat situ. Okay, so observe apa dia punya explanation pertama. CO2 has higher molar mass. Dan CO2 has higher molar mass, and then in terms of surface area, CO2 has higher surface area because of argon. You boleh imagine tak, argon tu dia satu atom saja kan. Okay, satu atom. On the other hand, CO2 dia ada carbon, dia ada oxygen and oxygen. So by right, the surface area is larger. Okay, so those are the factors that can contribute to stronger intermolecular forces for CO2. Okay, right. So the smaller the values of A and B, the smaller the correction and the more ideal the gas. So argon will behave more like an ideal gas than CO2. Okay, so smaller correction, so have smaller values. Okay, ataupun yang sama waktu dengannya lah, tak semestinya dalam bentuk smaller correction. Okay, so you smaller value of A and B. So smaller value of A shows weaker intermolecular forces. Okay, therefore it can behave more like an ideal gas atau yang sewaktu dengannya. Okay. Okay, so another example, if 1 mole of an ideal gas was confined to 22.41 liter at 0.0 degrees Celsius, it would exert a pressure of 1 atm. Okay, right, and then by using Van der Waals equation, so this, sebab dia mention dekat sini ideal gas kan, so this is the pressure of the ideal gas lah, of the gas when dia behave ideally. So that's why it is called ideal gas. So this is the pressure. So the pressure of ideal is 1.00 atm. Okay, so when we use Van der Waals equation, okay, we have to calculate the pressure. You have to calculate the exerted pressure by 1 mole of chlorine in gas state in 22.41 liter at 0.0 degrees Celsius. It's actually the same gas. Mestilah kalau nak compare, mestilah compare gas yang sama kan. So ideal gas ni adalah chlorine sebenarnya. Cuma this is when we assume that it behave ideally. This is where we consider the intermolecular forces and molecular volume. Okay? Alright, so the P real, okay, maksudnya dia bila dia behave sebagai gas yang dia deviate tu lah. Kita nak check. Dia deviate ke tak deviate? Okay, kita boleh check So by using Van der Waals equation, so kita pun calculate. So all the A and B, R are given. Okay, so this is the formula that you're going to be using. Okay, and then you insert all the formula, make sure that you substitute correctly. Okay, and then make sure. And then one more thing I would advise you, please write down the formula. Okay, just to let you know, okay, the more complicated the formula is, okay, the higher tendency for you to get mark just by writing down the formula. Okay, tulis formula je dapat markah. So, you rugi apa? Tulis je lah formula tu. Tapi make sure that it is the correct formula lah. Usually student akan mix up macam ni. N2A tapi dia jadi Na2. Dia tersalah tulis somehow. So bila dia salah lah semua So make sure that you have the correct formula. Okay, alright. So this is the formula. You insert, you substitute all the values, and then this is the final answer, 0.99 ATM. When we use Van der Waals equation, we got 0.99 ATM. So what can we conclude from these two values? Okay, this is using ideal, this is using Van der Waals equation. So as you can see, there is not much of a difference in terms of the value. So kita boleh kata that at this condition, at this given condition, the chlorine gas behave almost ideally. Okay, behave almost ideally. Kita akan compare. You try kira. That's why saya kata, you boleh je kira guna ideal gas. Tapi does that, dia describe the real gas accurately ke tak? Kita boleh conclude that the chlorine gas behave ideally at these conditions. Okay, so dia boleh behave ideally at this condition. Alright. Okay, so we have checkpoint 16. So I give you like 4 minutes for you to complete this checkpoint. Okay, and then we will discuss it. Okay, buat dulu. Tunggu azan eh. Okay, alright, so let's discuss the answer. The 3.5 mole of NH3 occupy 5.2 liter at 47 degrees Celsius. Calculate the pressure of the gas in ATM using the ideal gas equation and also the van der Waals equation. Okay, and then you have to explain why the pressure calculated in A different from B. Right, so this is for A. Okay, so the pressure calculated is 17.7 atm. This is for B. Okay, for the value of constant for A and B, you have to get it from the table, okay, from the previous slides, and then you can insert into the formula, okay, to find the final pressure. So as you can see, okay, if we were to compare between these two pressures, so the one that we have calculated using the van der Waals equation has lower in pressure compared to the one that we have calculated using ideal gas equation. Okay, so they're slightly lower. I would say significant lah compared to 0.99 dengan 1 atm just now. So this is 16.2, this is 17.7. Okay, why does this value different? Kenapa dia berbeza? Okay, cuba tengok jawapan dekat sini. based on the van der Waals equation, the intermolecular forces is more significant. Okay, alright. So dekat sini pressure dia decreasing to 16.2, and then from the value of A itself, okay, we could see that it is a very large value, okay, 4.17. Compared to B, it is 0.0371. Okay, so we could say that NH3 kan? Yeah, NH3 has apa nama tu, intermolecular forces ataupun the intermolecular forces present in NH2, NH3 is more dominant. Okay, is more dominant than the particle volume. Okay, dia lebih dominan dekat situ. Cuba tengok graf tadi. Okay, dia macam ni lah, ibaratnya graf ni macam ni, you nampak kan? Okay, dia punya explanation lah kenapa, explanation dia, the answer here. Okay. The intermolecular forces is more significant compared to particle volume. Okay, so that is why the pressure, when we use van der Waals equation, the pressure is lower as compared to when we calculate using ideal gas equation. Right? Okay, so that is all for real gas deviation. The deviation from ideal behavior. Any question from you guys?
Madam.
Yeah.
So maksudnya kalau soalan tu tanya pasal volume, baru jawab yang molecular volume tu significant daripada intermolecular forces.
Supposedly lah macam tu, because dia suruh calculate the pressures kan. Okay, you have to calculate the pressure. So you go for pressure lah. Okay, so you have to explain apa nama tu, why when we calculate between these two equation, they provide different answer. Okay, so the reason is because of the intermolecular forces. Okay, sebab kalau in terms of intermolecular forces, sebab kita cakap pasal pressure kan, kalau volume, so far kita tak pernah lagi lah ada soalan related to volume lah. Sebab volume tu, you nampak tak dia punya B punya value tu, dia kalau nak compare dengan A punya value, dia jauh sangat kan, beza dia kan. So that is why kita punya focus so far lah for our syllabus is more on the pressure rather than for the volume. Untuk volume ni effect, you in terms of graph, graph kat sini. Okay, tapi saya tak tahulah, mungkin creativity soalan yang keluar tu tak tahu macam mana dia twist soalan tu so that dia boleh tanya in terms of volume ke. Okay, so far kalau in terms of calculation memang we go for pressure. Using van der Waals dengan using ideal gas, and then you have to justify kenapa apa nama tu, using both equation they provide different answers. Okay, so kita.
Okay, madam, thank you.
Any other questions before proceed to liquid subtopic? Okay, tak ada kita tak ada, jom gerak. Okay, jalan. Okay, so next will be liquid. This is the last subtopic for topic 4. As you can see, we have a lot of learning outcome for this subtopic alone. We have 1, 2, 3, 4, 5. We have 5 subtopics. Okay, we have 5 learning outcome for this subtopic. Make sure that you cover all of this. Okay, once you have completed this subtopic. Okay, moving on. Corrugative properties of solution. Sekejap ya. Okay, colligative properties of solution. There are three colligative properties to consider. One is the vapor pressure lowering ataupun the Raoult's law. We use Raoult's law, okay, to describe this vapor pressure lowering. Then boiling points elevation, and we also have freezing point depression. So these are the colligative properties of the solution. Okay, sebelum tu saya hampir terlupa. Alright, so liquid, okay. Liquid in this case is not about the liquid itself. Dia sebenarnya is about the gas. Dia sebenarnya gas, tapi the source of the gas come from the liquid. Remember last time saya cakap pasal evaporation of the water kan? Water, okay, when initially it is water in liquid form, when the water, the molecule water escape from the surface of the water, okay, escape and then eventually become vapors. They evaporate, they jadi vapors. So vapors is actually gas. State dia adalah gas. Cumanya we use vapor to show that the initial state of the process is liquid. Okay, initial state dia adalah liquid sebenarnya. Tapi bila dia evaporate, dia become gas. Gas tu kita panggil vapors. Okay. Alright, so for this subtopic, dia bukan pasal the liquid itself. It's actually about vapors. Okay, dia nak ceritakan daripada liquid, dia evaporate and become vapors. Bila jadi vapors tu, it's actually gas kan? Phase dia tetap gas. So we want to know what is the pressure, what is the mole bila dia duduk dekat atas of the liquid surface tu. Okay, that's why kita punya focus in this subtopic is liquid, tapi it's not liquid itself, it's actually the vaporization that takes place. Okay, from liquid it is transformed into gas ataupun vapors. Okay, cuma yang awal-awal tu, initial tu, kita punya focus is more on the gas. Maksudnya initially dia memang gas. Contohnya oksigen. You pernah dengar oksigen liquid ke? Tak ada kan? Nitrogen ya, kita ada nitrogen liquid. What else? NH3. NH3 kan memang asal-asal dia punya initial state dia memang gas. Okay, so those tu memang dia punya originality tu memang in gas form. But for liquid punya subtopik ni, dia nak tunjukkan initially it is in liquid form. When it evaporates, dia jadi vapor. So what happened to the pressure? Bila dia jadi vapor, dia behave sebagai gas sebenarnya. Okay, so that is our focus for this subtopic sebenarnya. Okay, alright, so moving on. So we have colligative properties of solution. So what is colligative? Sebelum kita go into, there are three properties of colligative. There are three colligative properties. Okay, all of these three. What is colligative properties? Apakah itu dulu? Okay, colligative properties, it depends on the amount of solute. Okay, the amount of solute present in the solution. So because we are talking about solution kan, that means solute dalam solvent, betul tak? Solute dalam solution tu. So colligative properties ni adalah dia depends, okay, properties, okay, properties that depends on the amount of solute present in the solution. Okay, so the present of so the amount of solute present in the solution. It's not because of the nature of the chemical species ataupun the solute itself. It's just solely based on the amount, berapa banyak dia ada in the solution. That is all. Okay, so the presence of this solute boleh menyebabkan these properties, these colligative properties. Okay, it can cause vapor pressure lowering, it can also cause boiling point elevation, and it can also cause freezing point depression. So these are the colligative properties that is caused by the amount of solute present in the solution. Okay. So saya pun tak tahu kenapa dia tak include in the slide. Last time we do have the definition of colligative properties, but this time around so apakah maksud colligative properties? The amount, it depends on the amount of solute present in the solution. So these are the dia punya effect, okay, on the presence of the solute in the solution. Dia boleh menyebabkan vapor pressure lowering and so on. Okay, maybe you are familiar with you ada air and then you dissolve garam, you masukkan garam in the water kan, so dia jadi salt solution lah basically. It becomes salt solution. Okay, you know that when you add in garam, it will increase the boiling point of the solution, betul tak? It will no longer be, the water will no longer boils at 100 degrees Celsius. Instead, dia akan boils maybe at higher temperature, which is 101.3 ke 103 ke kan. Maksudnya dia higher than the temperature of the water itself. So that is what we call boiling point elevation, kenaikan takat didih. Okay, you juga mesti familiar with when we add salt, okay, to the ice, kita letakkan salt pada ice and it causes the ice to melt, not at 0 degrees Celsius, okay, tapi the freezing point ataupun the melting point become reduced to a negative value. Okay, tahu kan? Itu tahu kan? Benda-benda itu. Inilah colligative properties. Okay, so that is what we call freezing point depression. Maksudnya dia merendahkan takat beku. Okay, dia merendahkan takat beku. Dia boleh prolong lama. So those are the application lah yang you dah tahu tapi kita tak belajar in detail. Okay, so those are considered as colligative. Solution. So we have two types of solution. Okay, solution, we know that solution is consists of solute and solvent, and these two they combine, it will form solution. Okay, right. So solution, we can have two types of solution. One is solution with non-volatile solute. Okay. Alright, so opposite to this one, we have solution with volatile solute. Remember, it's because of the solute, the presence of the solute in the solution. Okay, alright, so we may have these two type of solution, non-volatile solute dengan solution with volatile solute. Kalau non-volatile solute, maksudnya solute tu, it will not vaporize. Okay, logically speaking, bila cakap non-volatile, that means it will not vaporize. Macam garam kan. Garam is considered as non-volatile solute. Okay, but that is another part of the story lah. Sebab garam dia ionic, dia cerita lain. Kita tak cover that one. Tapi itu boleh digunakan sebagai contoh. Okay. And then water is considered as volatile. Dia boleh vaporize. Okay, so kalau non-volatile solute maksudnya the solute will not vaporize, it will remain at the bottom. Okay, it will remain in the solution. Whereas kalau vaporize pun, the solvent will only the solvent will vaporize. For solution with volatile solute, dia terbalik lah with this one kan. That means the solute will also vaporize, not only the solvent. The solute will also vaporize. Okay, alright. So the vapor pressure above the solution. Can you imagine? Okay, you have a solution and then you tutup, then you cover the solution. Okay, so after sometimes the surface of the solution to the molecule on the surface of the solution will vaporize. Okay, will vaporize. So siapa yang vaporize? If it is a solution with non-volatile solute. Okay, so by right, the vapor pressure, the vapor pressure above the solution is due to the partial pressure of the solvent only. Okay, like I said just now, solute will not vaporize, solvent yang akan vaporize. So pressure dekat atas tu, bila dia vaporize dia jadi gas kan? dia adalah gas. Bila dia gas, dia ada pressure. Dia tetap ada pressure. So the pressure above the solution is caused by the solvent particle, not because of the solute particle. Sebab solute particle tak vaporize. Okay, alright. Opposite to that, the vapor, kalau solution with volatile solute, the vapor pressure above the solution is due to the partial pressure of both solvent and solute, because both of them vaporize. Both of them will escape from the surface of the solution and vaporize to become gas. So ada pressure lah dekat atas tu. So the pressure comes from both solvent and solute. Okay, that is the understanding. Dia logik je. Kat sini logik, tak ada masalah. Okay, this one solvent only. Okay, so let's look at the solution with non-volatile solute first. Okay, so since we have only solvent, okay, on the upper face of the solution, this produce a vapor which is pure solvent. So by right, vapor yang kat atas tu hanyalah vapor of the solvent saja. So kita boleh kata it is the vapor of pure solvent lah. Okay, because solvent saja yang naik. So kat atas tu hanya ada solvent sajalah. So we can consider it as a pure solvent. Okay, example, we have glycerol, glucose, sucrose. So these are all non-volatile solute, yang berat-berat, yang likat-likat, yang viscous. Those are considered as non-volatile solute. Okay, alright. On the other hand, a solution with volatile solute, substance with boiling point less than 100 degrees Celsius. So how do we identify whether it is volatile or is it non-volatile? Okay, normally if the boiling point of the substance ataupun the solute is lower than 100 degrees Celsius, we would say that the solute is volatile. The solute is considered as volatile. Okay, alright. So produce a vapor which is a mixture of both solvent and solute. It's actually benda yang sama kat atas ni, atas dengan kat bawah ni. Okay, alright. So example, alcohol, pentane. So these are considered as volatile. Okay, the temperature is lower than 100. Okay, alright. Okay, so this is the formula. Okay, right. So kita tak boleh nak guna kita punya pendekatan, our approach, if we are starting from the solution, you cannot just simply use PVNRT. Faham tak? PVNRT untuk gas yang memang dah dalam keadaan gas. Okay, dia sesuai untuk memang yang keadaan gas. Initially and after pun dia still in gas state. Tapi ini, we start from the solution. Okay, so starting from the solution, dia vaporize naik ke atas. So kita tak boleh guna PVNRT. We have to use Raoult's law. So Raoult's law describe on the vaporization of the apa nama tu molecule from the liquid to vapor state ataupun to gas state. So the Raoult's law is written as this. Okay, alright. So kita ada PA. PA is the pressure of A. In this case, A dia adalah yang volatile. Mestilah yang naik ke atas tu yang volatile kan. So mestilah dia represent the component that is volatile. Okay, katakanlah A is the solvent. B is the solute. Okay, alright. So we know that solute in this case is non-volatile. Okay, alright. So by right, so B is not vaporized at all. So to consider the Raoult's law, PA, the pressure of A, the partial pressure of A is equal to mole fraction of A in the solution. Okay, mole fraction of A in the solution times with pure, okay, pressure of pure solvent. Okay, pressure This one you ada note kat atas tu kan. Ni apa? Maksudnya pure. Okay, pure solvent. The pressure of pure solvent, which is A lah. Okay, which is A. So patutnya soalan kena bagi ataupun soalan suruh you cari. Either way pun you kena tahulah. P not A is actually the pressure of pure solvent. So imagine kalau solvent tu standalone. Okay, so these are all solvent. Maksudnya without the solute. So that's why we have pure dekat situ. Okay, satu lagi option. This is, imagine this is A saja. This is A plus B. Okay, yang saya colourkan ni, yang non-volatile solute. Maksudnya dia ni tak akan vaporize. Yang vaporize adalah yang A saja, yang tak colourkan tu. This one tak. Okay, yang vaporize only yang apa nama tu, yang putih ni. So A ni dia vaporize, so kalau kita cover dia akan ni maksudnya kalau dia stand alone. Okay, right. So this is what we call Raoult's law. Inilah Raoult's law-nya. And then how about for volatile solution having volatile solute? So by right, it should be the P total. The pressure should be the total of A and also B. Okay, so mole fraction of A, this is PA plus B, PB, ini KIV kejap Saya kurang tahu macam mana boleh dapat this one. Okay, mole fraction of A times P naught A is equal to mole fraction of B times P naught of B. Okay, alright. So ini kalau kita assume that both of them are volatile. So by right kat sini sebenarnya P total it should be P XA P naught A plus XB P naught B. Betul tak? Dia macam ni lah patutnya. Kita kembangkan je menggunakan Raoult's law ni. Tapi tak tahu macam mana dia boleh end up. Maksudnya assume that the P total is equal to 0. How in the first place dia dapat macam ni begini ni tak tahu. Okay, tapi so far dia beginilah. P total is XA PA naught times XP PB naught. Okay, alright, itulah Raoult's law je. Ni, this is the Raoult's law. Kita consider the vapor pressure. Okay, the vapor pressure. Raoult's law describe the relationship between vapor pressure, mole fraction and vapor pressure of pure component. Like I said just now, kalau dia stand alone, okay, only the pure component present. Okay, so how do you, so this is the formula of the Raoult's law. Okay, vapor pressure of partial pressure of component A above the solution. P naught A pula, vapor pressure of partial pressure of pure component A, maksudnya only the solvent is present. Okay, so assume that all of these are pure solvent. So yang naik of course lah the pure. Okay, alright. So the first step is to make sure what type of solute do you have in the solution. Is it non-volatile solute or is it volatile solute? If it's non-volatile solute, that means you should have solvent. Okay, that you should only have solvent in the upper phase of the solution because the non-volatile solute will not vaporize. Kalau volatile solute, that means you should have both on the upper phase of the solution. So you kena total lah dekat situ. Okay, using this Raoult's law. Okay. Alright, so buat apa saya ni? Alright, so let's just stop here. The rest we will continue tomorrow. Okay, any questions so far related to liquid colligative properties of the solution? Ada ke?
No.
Ada. Okay, all right. If there is no question, I think that's all for today's lecture. Okay, all right. So thank you everyone for your for your ears. Okay. And your cooperation is very much appreciated. Okay, so that is all. Okay. Assalamualaikum.
Thank
And
you, madam.
Thank you, madam.
Thank you, madam.
Thank you, madam.
Thank you, madam.